Okay, so now that we have agreed that we'll use probability to model our guess list and the likelihood of different guesses in our guess list, we need to review some basic probability. So I assume that you have all taken some course in probability, at least an undergraduate level course in probability, and have seen concepts such as probability mass functions, probability density, probability distribution, random variables, expected value. There'll be some other inequalities which we will be covering in this review: Markov inequality, Chebyshev inequality, law of large numbers, central limit theorem. And while I don't assume that you know these things thoroughly, but I expect that you go ahead and read about these from some books. So I'll cover these things very briefly and very quickly, mainly to agree on the notation, and then I expect you to go and read them. So then this first part of my review, I'll basically cover, this is the first part. And in this first part, I'll cover notations for, let's say, probability and expectation. And let me start right away with the warning. This is not a course in probability. So here is a warning. So I'll do very little things. I'll do very few concepts and little knowledge. May be dangerous. And so I urge you to go ahead and read the basics on your own. Okay. So with that caveat, let me start my quick review of probability. So as you may know, there are two kinds of probabilities that we encounter. One is discrete probability and one is continuous probability. We see discrete distributions and we see continuous distributions. And we talk about probability mass functions and we talk about densities. So let me start by reviewing a common notation which will unify both of these into a single umbrella. So for us, the probability, when we talk of probability, we take a set. We talk of a set, which is the universe where all things are happening. So for us, that universe is this set X. Okay. Let me clean up the screen a little bit. Let's see. Okay, right. So for us, that set is this X. And this is where all our events take place. This is the set of guesses for us. Remember? And an A, which is a subset of this set, is called an event. And we assign probabilities to this event. A probability mass function assigns a probability mass P to each element in this event, whereby the whole event gets probability which is sum of all the Px. Okay, that's something which you may be familiar with. So this Px is the probability mass function. It puts a probability mass on each X. For example, if this universe X is just the coin toss, so it's just heads and tails, so then this X can either take the value heads, which has some probability 0.1, let's say, and then tails will have probability 0.9. And so this Px can have those probabilities 0.1 or 0.9. Okay. In general, we use this notation small px for probability mass function evaluated at X. And the probability of a set A, which is a subset of X, so an event A, is just the sum of probability mass function over all elements in A. That's the definition of probability. That's how this probability mass function can be used to calculate probabilities of events. So there's something which I assume you know. Let me write it in a different way. So instead of writing this as a summation over this X in A here, I write it as summation over all X. But I multiply this thing with an indicator function here. So this thing here has a name. It's the indicator function. Indicator function of A. So this function takes X as input and output 0 or 1. When X belongs to A, the output is 1. When X doesn't belong to A, the output is 0. So it's the indicator function of A. So what we notice here is something very simple, that this summation can also be written as summation over x, px times indicator function of a. Okay, it can be written in this form. Okay, so this is one observation we make. Now let's move on to continuous probability distributions, in which case we talk about probability densities. Okay, so now x is a continuous set. For instance, x can be the d-dimensional Euclidean space Rd, or it can be even more complicated sets, such as set of functions which have frequency domain response between some band limited thing. So such functions, for instance, appear when you are thinking of communication over real channels. So this can be a very complicated set X. But let's, for concreteness, think of a very simple set, just a d-dimensional Euclidean space. So that's a continuous distribution. For d equal to 1, this is just the real line. And we again want to talk about probability of events. Events are subsets of this Rd. Probability of an event now is the integral instead of summation of this density. So this Px will be called probability density. It's the integral of probability density over the set A. So once again, just like we did it here, instead of writing it as integral over A, we can write it in this form, integral over the entire space, but multiplied with an indicator function of A. It's the same thing, it's the indicator function of A. So in this sense, you can see that densities and probability mass function look very similar, except that here we are computing an integral with respect to the Euclidean space, and sometimes it's called integral with respect to the Lebesgue measure. Okay, and here we are computing a summation, which is also a kind of integral, by the way, but over a very simple measure, the counting measure. Okay, so these two have a very similar form, and that's the connection between density and probability mass function. They can both be used to compute probabilities of event by integrating Px times the indicator function of an event over using the underlying measure. Here it's the Lebesgue measure, here it's the counting measure. Okay. For some notation, so as we said, both definitions of PA, probabilities of events, have a common expression. They look like this: PA equals to integral of indicator function with respect to some measure, and we will use a small abbreviation for this this integral. Instead of every time writing integral px dx, we will simply write d of px. This is a standard notation actually. It means it's an infinitesimal probability measure. Just like we take very small length, this is the probability of a very small event, that single x. And we can write this as integral of over a of dpx. So this is some notation. P of a we are writing as integral over a of dpx. When when the random variable is discrete, then you should think of this integral as summation, and you get this. When the random variable is continuous, then you should think of this integral as an integral over a real line or Rd, and you get this. Okay, so this is a very quick review of a sort of a measure theoretic view of probability, but this notation is very important for us, and it also helps us handle both discrete and continuous random variable in a common framework. So if you are a little bit uncomfortable with it, I will suggest that you read on probability densities and probability mass functions and how they play a role in computing probabilities of events, which is what we are doing here. Okay. So let's now, so we have agreed on this notation. Let's now move to the next concept I would like to review quickly, which is the concept of a random variable. So we already saw a random variable, by the way. We saw this indicator function of A. This function takes as input element x and output 0 or 1. Okay, and we also define this particular integral, which is the integral of indicator function of a over dp. This is just a notation we introduced. We saw that this is equal to p of a. That's how this integral was actually defined. So you can think of this indicator function of a also as a random variable. This is a very simple random variable. It just takes two values, 0 or 1. And it tells you if that event occurred or not. So for instance, if your underlying probability space is that of a 6-sided die and you're rolling a die, a random variable that we can think of is this indicator function of a, where a is just the even numbers, 2, 4, 6. Okay, And in that case, this random variable will be again binary. Will take value 0 or 1. When an even number appears, the value will be 1. When an odd number appears, the value will be 0. Right? And we can define this integral, which is the probability of an even number appearing, which is just half. Okay. So if you agree with this definition, and if you agree that we can define all such indicator functions for all such events A, then what we can do, we can also define this linear combination of such indicator function. So this is some weight AI times indicator function AI. So we can define all that, right? And then you may ask, that's fine. Now what is this integral which was earlier just P of A? So let's assume that we can take this summation outside the integral. In fact, that's how this integral is defined, that you should be able to take summation outside. So an integral is defined in such a manner. And it's a linear operation. That's all we are saying here. So this summation can be taken outside. And therefore, this integral here becomes summation I equal to 1 to L AI P of AI. Okay. That's the integral of this guy. So my claim is this is also another random variable. So we started with a very simple example of a random variable, which was this indicator function, which just takes two values. And we can combine some of them, take their linear combination to get this new random variables. Many of them now. Each linear combination gives a new random variable to us. Okay. So you have done this. Now we are not allowed to use any subsets A that we want in general. There is a subtlety to this, and you have to take a formal course in real analysis or probability theory to figure out which subsets A are allowed. But a large class of subsets A are allowed. Okay, and all these are your events. And you can take indicator function for all these events and take their linear combinations and get new random variables. Okay. In fact, when X is discrete, then all subsets are allowed. So if X is discrete, then all subsets are allowed. The subtlety that I'm talking about appears when X is not discrete. For instance, if you take X as this interval 0 to 1, you can start by allowing all intervals. Okay. And then this, for an interval, the function looks like this. Indicator function, it's 0 everywhere here and it's 1 here. And you can take this linear combination, such functions will look like this. Okay. So all such functions, so let me take some space here. So such functions, so these look like this, right? Summation over I, AI, indicator function AI. Such functions we are taking into account. So what is the domain for this function? That from X, and this is the same as the probability space X, where our basic events are taking place, and they take values in R. Okay, since you're taking linear combination of R, it remains R. You can make it complex numbers. For this course, R suffices. Such functions are called random variables. Okay. And so till now we started with very elementary function, indicator functions of events. Then we take their linear combination, we get a richer class of functions. And now what we can also do is we can also take limits. Okay, we can take limits so that this integral f can be defined as limit of such integrals here. Okay, so we can even take limits, and there is a technical way of doing all this. But roughly speaking, all such functions which arise from such limits are called random variables. So what was this procedure? What did I just walk you through? So let's draw some analogy with how you construct real numbers. We first learn natural numbers. So natural numbers are, formally they are some kind of an inductive set which contain 1. But one easy way to think of natural numbers is just, they're just counting numbers 1, 2, 3, 4. And then from natural numbers, we move on to fractions. Okay. So we learn fractions, rational numbers. And then we learn that these rational numbers are dense inside the real. And if we take the limits, then we'll fill all the gaps in the real line and we'll get the real line. It's a similar procedure. We first define the simplest of the numbers, this indicator function of events. These are sort of like our natural numbers. Then we took this linear combinations. These are sort of like our rational numbers. And then we took limits. And those limits are real numbers. So we have made this large space of functions which we call random variables. This way. Also, using the same procedure, we were able to define this integral f of tp for any random variable f. Okay, and it's just defined as a limit procedure. And this function you have seen before. Okay, so I'll come to this function, this integral of a function f. So just as a summary, a random variable is such a function f, just like the one we got above. It takes values in this real line r. So, but the probabilities, remember, were on the domain of f. Probabilities were not on the range of f. And we denote these random variables by capital X. And this integral, so instead of f, we'll denote it by capital X. This is the same as your f. It's the f of whatever the input was. Okay. And so now we remember we were able to define this integral because that's how we constructed a random variable. This integral is something which you may be familiar with. It's called the expected value of x. So whenever we have a random variable, we can talk about its expected value. It's denoted by expected value of x. This notation here. So this notation is something I'll use throughout this course. So I may have taken a concept which you already knew and have confused you about it. What I'll request you to do is to brush up your probability, read about random variables, read about expected value of a random variable, and then come back to this lecture and try to see if you can make sense of what I just said. If you can connect the concepts that you already knew to the way I described them, because this is perhaps an alternative view for some of them. This is the measure theoretic view of probability, and it really helps us in writing formal proofs, and generally it's a good way to unite both discrete and continuous probability. Okay. So we were talking about these random variables. What about this elementary random variable? Okay, the random variable, the indicator function random variable. Turns out that this random variable has a very useful expected value. Expected value of indicator function of A is simply the probability of A. Remember, we can only talk about probability of this event A, but from this we would like to talk about probabilities of this random variable taking some value. So suppose what's the probability that random variable x, which is now a function, takes values in B. That probability is the expected value that the domain of x is so that the output belongs to B. So this is what we are writing as indicator function f inverse of B. So it's just the probability of f inverse of B. That's what that probability is. Okay, so this is some quick review of random variables. So we have, I expect you to see some random variables. I expect that you have seen some random variables: Bernoulli, binomial, Poisson, geometric, Gaussian, exponential. The last two here are continuous. The first four are discrete. Maybe I'll walk you over some examples so that I can make the discussion I had just concrete. So let me just do that. Let me go to the side screen and walk you over some examples. All right. Okay, so let's just work out some examples. So examples of random variables. Okay. So I hope that all of you have seen this most basic random variable for which the sample space x is just 0, 1. And remember I said that this f of x is the random variable we have to talk about. It's just x. Okay, that's my random variable. This one is called the Bernoulli random variable. It's just a different view of Bernoulli random variable. Okay, and when I talk about this, I also have to talk about probability of different events. So I only need to talk about probability of 0. Let's say it's 1 minus p. Then the probability of 1, which is the complement of the 0, is just p, because total probability must sum to 1. And from that I can compute the probability of even the empty set. It must be always 0, right? So this random variable x is called the Bernoulli random variable, and when we talk of random variable, we typically we describe them by their distribution. So I will use the notation that x is distributed as Bernoulli p. So it takes two values, 0 and 1, and the probability that it takes value 1 is just p, small p. Okay, so what is the expected value of this x? right? So it's a discrete random variable. So this particular expectation, which is an integral in general, that's what we just established, can be written as summation over different values that this random variable takes. Okay, so y and probability of that value. So this random variable can just take, I'll write it in new form. So summation over y is a discrete random variable. Probability that x takes the value y times y. So in this case, this is just takes two values. So probability that x takes the value 0, this is my notation for that, times 0. So this guy doesn't matter. Probability that x takes the value 1 times 1. So this is just p. Okay. Another way to see the same formula is that this random variable x here, okay. So this random variable here is simply the indicator function of an event. That event is what? What's that set A? That set A is just 1. So this is 1 when x is in 1 and 0 otherwise. And therefore its expected value is simply probability of 1, and which is p. That's something we saw, right? So this is a very basic random variable, Bernoulli. Okay. Similarly, I can do another example. You can think of a binomial random variable. Okay. Now, so from now on, we will not worry about the underlying space x as such. We will directly think of the random variable and the place where it takes value. So this particular random variable can be thought of as sum of n independent Bernoulli random variable. So n independent coin flips. So I'll call it y. It's just x1 plus x2 plus xn, and this x1 to xn, all of them are independent, and each xi is distributed as Bernoulli p. Then we say that y has a distribution which is binomial with two parameters, n because I'm adding n independent Bernoulli random variables, and p because all of them have expected value p. So what is the expected value of y? Well, expected value of y is expected value of x1 plus xn. So this linearity of expectation is a property which I want you to use very frequently. And this guy can be written as summation I equal to 1 to n expected value of xi. Each of this is p, so it becomes n. Okay. So I just want to do two examples quickly. And another example which you can work out is that of a Gaussian random variable, which is a continuous random variable. Okay. So yeah. So for now, I'll just continue. I just wanted to cover these two examples. Let's see. All right. Let's clean up the screen a little bit. Okay. So we just learned of random variables. So now what we will do, we'll model our unknown answers by random variables. Rather than thinking of x as a set and thinking of it having probabilities, we will think of the unknown answers as a random variable. That's what we will do. So we learned about random variables, we learned about expectation, and then we decided that from here on, we'll model our unknown answers, that guess list, by a random variable. So we'll behave as if that unknown answer that we all want to know is a random variable with certain distribution. Now, who gave you that distribution? That distribution is a belief that you're putting on that random variable. Alright, so this is our premises from here. So I'll stop with this part and then continue with the next part of the equation.